Okay, so if you've ever, really thought about the universe, the big rules, you hit this wall, right? Special relativity. Einstein says nothing with mass, absolutely nothing, can go faster than light speed, Seattle.
Yep.
But then you hear the universe itself is expanding faster than Theta. How does that even work? It feels like a direct contradiction.
It totally sounds like physics is breaking its own rules, doesn't it? But the paradox, it kind of dissolves when you realize we're talking about two different kinds of speed, two different arenas. There's the local stuff, motion through space, governed by special relativity, and that strict speed limit, c$. And then there's the global picture, the stretching of space itself. That's general relativity territory. Untangling those two. That's really our goal for this deep dive.
All right, let's nail down that local speed limit first. Why is TL this ultimate unbreakable barrier? I mean, why can't you just keep pushing something faster and faster?
Yeah, it's fundamental. It's not just like a speed limit sign somebody put up. It's woven into the very fabric of space-time, according to special relativity. The core reason, physics. As anything with mass gets closer and closer to light speed, its inertia, its resistance to going faster, it just climbs. It heads towards infinity.
Ah, right, the relativistic mass idea. So the energy needed just blows up.
Exactly. You'd need an infinite amount of energy to actually reach t$, if you have mass. It's physically impossible based on 1 dia MC2 and it's deeper than just motion. t$ is also the speed limit for information, for causality. If you could beat it locally, you could, well, mess up cause and effect.
Yeah.
Send signals back in time, the whole structure unravels. So yeah, that limit is absolutely firm locally.
Okay, local rules clear. But now we zoom out. Big picture. You said we switched from special relativity's rules to general relativity, where space isn't just a stage, it's dynamic.
Precisely. General relativity describes gravity as space-time curvature. And on the very largest scales, the universe's solution to Einstein's equations involves this thing called metric expansion. Space itself is stretching. Think of it like, well, the common analogies are dots on an inflating balloon or raisins in rising bread dough. The galaxies aren't really flying through space away from each other over these vast distances. The space between them is growing.
Right, the balloon or the bread, I get that visual. But those analogies always felt a bit off because raisins can move through the dough, right?
Yeah.
Locally.
That's a really important catch. Yes, the analogy breaks down there. This expansion is only really significant, only measurable over huge cosmological distances. Millions, billions of light years locally. Like within our galaxy or even our solar system or, holding you together. Gravity and electromagnetism are way, way stronger. They completely overwhelm that cosmic stretch. Your atoms aren't expanding, thankfully.
Okay, thank goodness for that. So, back to the main puzzle. We see a galaxy way out there, and we measure its recession speed, and it's, say, 1.5 times the speed of light. If $10 is the absolute local limit, how is that allowed? It still feels like cheating the system.
It feels like it, but it's allowed because we're conflating two different velocities. There's motion through space, which we call peculiar velocity. That's like Andromeda moving towards us. That stuff, absolutely limited by Cezanne, no question. But the speed you're talking about, the one derived from the redshift of distant galaxies, that's recessional velocity. It's an apparent speed caused purely by the stretching of space between us and the galaxy.
And that's linked to Hubble's law, right? The further away, the faster the recession.
Exactly. $vi equals h times distance. Since it's proportional to distance, if you look far enough away, well, beyond a certain distance called the Hubble radius, the amount of space stretching per second adds up to an apparent speed greater than $.
Ah, so the key is, it's not the galaxy moving through its local patch of space faster than light. It's the space itself expanding globally.
That's the crucial distinction. Recessional velocity isn't a true velocity in the special relativity sense. It's a measure of the expansion rate of the universe's fabric. And that expansion, space stretching, isn't bound by the local speed limit $.
Okay, that clarifies the how. But now, things get even weirder, right? Because the expansion isn't just happening, it's accelerating. Dark energy pushing things apart faster and faster. This creates something called the cosmic event horizon. What does that mean for what we can ever hope to see?
Yeah, this is maybe the most profound consequence. The accelerating expansion creates this boundary, the event horizon, roughly 16 billion light years away right now.
Yeah.
Think of it as a point of no return for light. Any galaxy currently beyond that horizon is receding from us so fast due to the combination of distance and accelerated expansion that light emits today. Even traveling toward us at speed c$ will never overcome the stretching space between us. It will never, ever reach Earth, not in a billion years, not in eternity.
So we can see the light they emitted billions of years ago when they were closer. But their present, their future, it's causally disconnected from us forever.
Precisely. We see their past image, but we can never receive any new information from them from this point forward.
Wow. And the implication, if acceleration continues,
Yeah.
is that eventually all the galaxies that aren't already gravitationally bound to us in our local group, they'll cross that horizon.
That's the long-term forecast, yes. They will effectively vanish from our view. Their light will redshift further and further until it's undetectable. Imagine astronomers billions of years from now. They might look out and see basically nothing beyond our local cluster of galaxies, a vast, empty void. They might conclude they live in this small, isolated island universe with no clue about the Big Bang or the cosmic web we see today.
So we are living in a special time, a privileged cosmic moment where the evidence of the universe's grand history, the distant galaxies, is actually still visible.
It certainly seems that way. It suggests that cosmology, the study of the universe's origin and evolution based on observing distant light, might actually have a finite lifespan.
What a thought. Observational cosmology having an expiration date. So remember, next time you ponder light speed, keep the local rules separate from the global canvas. The limit holds. But the universe itself is playing a much bigger game.